Welcome back, everybody, to the High Performance Fundamentals YouTube channel. I'm Lawrence Snyder, and this will be the third video in my Automotive Electrical Systems video series. Today we'll be covering wattage, joules, voltage and amperage, and their relationship to power. Throughout this video, I'll be providing multiple examples, analogies, and calculations. But before I get started, I'd like to take a few minutes to make an addition, and a correction to last week's video on series, parallel, and series parallel circuits. The addition will be a simplified explanation for Kirchhoff's circuit laws and why it's relevant when you're making circuit value calculations. So here it is, Kirchhoff's circuit laws. There are two of them, the first one being Kirchhoff's current law, the acronym for that is KCL. The second one being Kirchhoff's voltage law, the acronym for that is KVL, and Kirchhoff's voltage law is also known as Kirchhoff's loop rule. Okay, so what are they and why is it relevant? Why do you need to know? Okay, so the definition for Kirchhoff's current law, and this is my simplified explanation or simplified definition, is the sum of the total circuit amperage. The sum of the total circuit amperage is equal to the sum of the individual circuit or circuits amperage or amperages. Okay, that's Kirchhoff's current law. Now, Kirchhoff's voltage law, the definition for that, or the simplified explanation or definition, is the sum of the circuit supply voltage is equal to the sum of the individual circuit's voltage drop. Okay, the sum of the circuit supply voltage is equal to the sum of the individual circuit's voltage drop. Okay, so why is that important? Why are they important? Kirchhoff's current law, Kirchhoff's voltage law, those are known as Kirchhoff's circuit laws. So we've been performing calculations on resistance, amperage, voltage drop, complete circuit calculations for series, parallel, and series parallel circuits. Why this is relevant, and I have a simplified version of this for this reason. This video series is not going to dive into manufacturing engine control modules. You're not going to make your own computer through this video series. So the in-depth calculations that you can run into utilizing Kirchhoff's circuit laws are not going to be displayed in any of these videos, because this video series is not about that. This is not an electronics engineering video series. This is based on automotive technician level, fabricators, DIY level. You want to build your own race car, you want to build your own hot rod, you want to make your own electrical circuits, you want to know how to do it correctly. That's what this video series is really about. We've gotten kind of technical up to this point, but you've got to know some of the basics and some of the equations. You know, you have to have that knowledge base to build on. So we've got to get through this to move on to videos that are more I don't want to say simple, but are more straight to the point, whether it's, selecting wire size or gauge or type of wire, or whether you're selecting a battery or whatever it is you might need to select to create your circuits. That'll follow, but we got to get through some of the technical stuff first. So how is this relevant? All right, so I want to break it down even a little bit further to say that all circuit amperage is accounted for in a circuit, and all circuit voltage is consumed. So let's just say that Kirchhoff's circuit laws, what they're saying is that if, for example, a circuit has 12 amps, if you know the circuit has 12 amps, it's a known value, you've measured it as 12 amps, or you've calculated it at 12 amps, as you break down the circuit, whether it be a series parallel, or a parallel, as you break it down into a single leg or multiple branches or multiple legs, the individual values for amperage, let's say 4 on this leg, 4 on that leg, and 4 on this leg, or 4 on all 3 branches, let's say, that'd be a total of 12. Your calculated value for amperage in that circuit better be 12, right? So 12 flowing through the circuit was your calculation or what you measured, and as you've determined the individual amperage through each individual leg of a circuit, the combined total should equal 12. So let's say 12 in, 12 out. So in like an algebraic calculation, it would be positive 12 equals negative 12, or positive 12 plus negative 12 equals 0. So all the amperage in the circuit is accounted for. Okay. Now the reason I say that is because this. When I had the water tower analogy in the other two videos, the past two videos, we showed that although the water pressure had gone to zero or darn near zero, it was still flowing. Well, amperage is like that. So amperage in the circuit flows through the circuit and actually flows back to the battery. It continues to flow. It's a big loop, right? Kirchhoff's loop rule, for example, right? It's a loop. It flows straight through. It loses its pressure by the time it's on the ground path or the negative side, or what they call the common side of the circuit, past all the loads back to the battery. There's no voltage. You won't calculate or you won't measure any voltage or calculate any voltage there, but there will still be amperage flow. But the amperage flow through the circuit is all of the amperage flow in each of the legs combined, or the sum of them. So basically, Kirchhoff's current law is just saying the sum of the total circuit amperage is equal to the sum of the individual circuit or circuits amperage or amperages. So 12 in, 12 accounted for, back to the battery, right? 10 in, 10 accounted for, back to the battery. If you do the calculation and you don't have 10 accounted for, but you're showing 10 flowing through it, you've made a mistake. If you're showing 12 accounted for, but you've calculated that you only have 10 flowing, then you've made a mistake. Right? And that's the idea, and that's the relevance as far as these equations are concerned. Now, let's move on to Kirchhoff's voltage law. Same thing, but in this case, all circuit voltage is consumed. Not necessarily accounted for, but consumed. So that if you have 12 volts of voltage pressure supplying a circuit, then leaving the circuit back to the battery, let's say, will be zero. You have consumed it all. As opposed to amperage, it flows through the circuit and back to the battery. On voltage, on the voltage side, remember we said voltage is like pressure. Right, like the water tower analogy, although the water is flowing from the exit side of the water tower, right, the pressure is very little or non-existent. Think about that water tower and an opening at the base of the water tower flowing out into a big field, right? Water's flowing through the field and it's being dispersed, right? Okay, but the reality of it is it has no pressure. It's still flowing, but there's really no pressure, right? So that's kind of like voltage. So in this situation, Kirchhoff's voltage law, or also known as Kirchhoff's loop rule, states that the sum of the circuit's applied voltage, let's say 12 volts, will equal the sum of the individual circuit's voltage drop. And in previous video, last video as a matter of fact, we did calculate voltage drop, and we showed that if 12 was coming in, the voltage drop at the end of the circuit the total was 12 volts. So at the end of the circuit it was 0 volts, supply voltage was 12, total circuit drop was 12 volts, all of it was consumed. So Kirchhoff's circuit laws, one more time, all circuit amperage is accounted for and all circuit voltage is consumed. It's relevant because when you make your calculations, you know what your calculations should equal to. As you calculate, if your values are wrong, you'll know. Okay, this is how you'll know. All right, and this is why it's relevant. I did touch on it a little bit. I talked about Kirchhoff's current law a little bit. When I was speaking about amperage, that would have been accurate, but I also mentioned, I brought that up again, Kirchhoff's current law, but I was talking about voltage, and that was inaccurate. So when I went back and watched the video over, I realized that I'd made a mistake, and also that I really need to dive into that a little deeper because it is relevant. I kind of glassed over it, kind of just, I guess, glazed over it, and I didn't give it enough I should have put more relevance into the explanation of it at that time, and I didn't do it. So I want to do it now, and I want to do that moving forward. Whenever I find an inaccuracy in a video after I watch it back, the second time or whatever, if it comes to me or if I catch something, then I want to update it on the next video. That way, if you watch one of my videos and you see something doesn't look right, or maybe you know something isn't right, look for it in my next video, in the opening of my next video. If I don't express it, if it doesn't come up, then I didn't catch it. And if you catch it, put it in the comments and let me know, and then we'll address it. Because I want this content to be accurate. I don't want it to be inaccurate, and I don't want it to be misleading in any way. I want you to learn from it. I want you to know what I know. So, and I want to be as helpful as I possibly can. All right, so now, I want to make a correction to last week's video. The correction is this. I had a bunch of different equations posted up here on the whiteboard or off to the sides here. And one of them I found after going back through it and watching it again, it hit me like, that's not right. As I was watching it, it's just a light bulb moment, whatever, and I said, that isn't right. And sure enough, I was showing the parallel circuit unknown resistance calculations, calculating for an unknown resistance. And then sure enough, the 2 resistor circuit calculation, I had put the resistance total minus the first resistance or resistor number 1. The reality of it is that should be resistance total multiplied by resistance 1, not minus or plus or anything like that, a multiplication factor. So, like I said, this is wrong, but one more thing I want to point out, and I didn't point this out before. You see how this says RT for resistance total or total resistance, right? You'll see that several places here, RT. That's accurate. RT is accurate, but you also will see, this as you look through, literature or whatever at any time in the future. You may see where it says R with a lowercase EQ, and that means equivalent resistance. Both are accurate. They could be replaced one with the other. So whether I were to have RT here or REQ, it wouldn't matter. It'd be the same thing. So I've always used RT, maybe just because it's simpler. But think about equivalent resistance or total resistance. It's basically the same thing. We're saying basically the same thing. But both will be accurate in this situation. Okay, with that being said, I feel as though I've kind of wrapped things up for last week's video. And hopefully I caught everything that was wrong. But like I said before, if you catch something you find is inaccurate, put it in the comments below. I'll either answer your comment, maybe you're incorrect, maybe I'm incorrect, but I'll answer it if I see it. And then if it is something we need to address, we'll address it on the following video. Okay? With all that being said, thank you very much for your time. And now let's get on to the content of this video. Okay, so let's get into this. In our very first video and our second video and in subsequent videos, we're going to talk a lot about Watt's law, Ohm's law, and we will touch on Kirchhoff's circuit laws again. But Ohm's law and Watt's law are involved in all of your equations when it comes to electrical system fabrication or design or diagnostics, what have you. So you have to know those, and in order to cement those in your memory, we're going to be bringing them up a lot. And I have to perform the equations I'm going to show you, or the calculations anyway. So what we had stated in the very first video, we went over Watt's law, right? And we converted power to watts. And we converted voltage, not a conversion, but it's a direct correlation. Voltage is obviously voltage. Current intensity is amperage. So we modified it to be, instead of P equals V times I, power equals voltage times current intensity, we made it wattage equals voltage times amperage. Okay, so what we know then is that when we talk about power, we're basically saying watts, right? It's the same thing. One is the other. Right? One is simply a unit of measure or calculated unit to explain power. Okay? So what I want to do is I want to break down, I want to reinforce that a little bit further. I want to give some analogies, and in order to explain more thoroughly what is power, what is work, what is force, what is velocity, what do these mean? Okay, it's great to have it up here, and it's great to put it in writing, and it's great to have the calculations, but it's better in my mind if you can actually understand what those things mean. So I got my very first analogy for you. I call it the concrete carry analogy. Okay, it's going to involve 3 individuals carrying concrete, and I'm going to explain this in a way where I believe will be easier to understand. So for example, let's just start off where power, right, we're trying to define for power, equals work per unit of time. I could just leave it at that and we'll call it a day. Work equals work per unit of time. That equals power, right? That's the meaning. I don't know. That doesn't really help me a whole lot in thoroughly understanding that. So let's break it down further. Work is equal to force times displacement. That helps a little bit. Force times displacement. Okay. And then power equals force times displacement divided by time. Okay, like I said, that's not that hard to understand, but that's why I come up with these analogies. Analogies have helped me a lot in the past. When I'm trying to understand something, I usually try to exaggerate it, or create an analogy, something in like my everyday life that I can wrap my mind around, that helps to cement, no pun intended, cement these equations into my memory. Alright, so the concrete carry analogy involving 3 individuals. So let's say that there's 3 of us, my good buddy Joe, my good buddy Stan, and myself. Let's say that we all are physically identical. We are the same height, we are exactly the same weight, We have the same inseam, our legs are the same length, everything about us physically is identical. And let's say that we're going to carry 2 big bags of concrete on our shoulders. All the bags of concrete all weigh the same. And the challenge is for us to carry those 2 bags of concrete from ground level, right, up a flight of stairs to the landing or to the top of the stairs. Let's say that, just for clarification's sake, let's say there's 30 steps in that flight of stairs. So now we know that all 3 of us have to carry 2 large, equally weighed bags of concrete up 30 steps, 1 flight to the landing, at which point we will set those bags down. Okay? So now we're going to do that. We're going to time it. See how long it takes us to do it. So sure enough, we start the challenge, and all 3 of us, we carry the weight and we set it on the landing. All 3 of us get the job performed. We did it. All 3 of us. So what do we know? Right? What we know is that although that is not the definition of power, it is a definition of work. We carried the same amount of load, right? The same amount of force was applied by all 3 of us. We displaced the load the same distance, right? So we did the same amount of work, all 3 of us. But there's a catch. Joe did it in 2 minutes. Stan did it in 4 minutes. And well, unfortunately for me, I did it in 8 minutes. So what does that mean as far as this calculation? So first off, we said that we all 3 of us performed the same amount of work. We did the job. We completed the task. We used the same amount of force and displaced the load the same distance, whether that load be the concrete or the concrete plus our physical body weight or mass. We had to utilize the same amount of force because we were able to perform the task and displaced the load the same distance. So same amount of work. But Joe did it in 2 minutes. Stan did it in 4 minutes. I did it in 8 minutes. So Joe did it twice as fast as Stan. He did it 4 times as fast as me. So the equation then would state that we performed the same work, but Joe did it in 2 minutes, I did it in 4 minutes, Stan did it in 4 minutes, I did it in 8 minutes. So what that means is this. When we calculate the power, Joe had twice as much power as Stan, and he exhibited 4 times as much power as me, which means that I exhibited half as much power as Stan, or 25% as much power as Joe, right? So you can see that, yes, we all performed the same work, but since Joe did it so much quicker, he exerted or exhibited a lot more power, right? So think about that. Okay, so I believe that for the first part of this breakdown of watts equals power, where we say that power is equal to force times displacement divided by time, that analogy gives you a pretty good idea as to what we're talking about here, the difference between work and power. Because we said that watts equals power, power equals work per unit of time, and then basically created an analogy where we perform the same amount of work but at different amounts of time was measured, right? So like I said, one guy did 2 minutes, one guy did 4 minutes, one guy did 8 minutes. So that's that. But then we can keep on going. So since we know that force equals displacement divided by time, right? The definition for velocity is displacement divided by time. So the velocity, like for example, like in a car, how fast you're going, kilometers per hour, miles per hour. The car travels a certain distance in a certain amount of time, right? So we have a speed calculation or velocity, right? So in this equation, for example, we also had a velocity. Since we know the distance from the ground floor to the top of the steps and the amount of time it took, we can actually calculate the velocity, like how fast he was going. Right? Now, we don't have to do that necessarily to understand what power means, but it can be calculated. This is going to be utilized later in this video because I'm going to perform a calculation on the board for horsepower. And horsepower, if you think about it like an internal combustion engine or an electric engine, or electric motor, I mean, it's not so easy to understand because, let's say, for example, an engine that's developed a certain amount of horsepower, it's not traveling a distance per se, right? It's not necessarily carrying a load per se. It's not as easy to wrap your mind around that. But we're going to utilize a horsepower calculation for this definition of power of force times velocity. And I think at that point, it'll make it a lot clearer. So watts equals power. power equals force times displacement divided by time. Watts would then therefore equal watts equals force times velocity. So this is accurate, and so is this. And that's just an overall definition of what watts are. Okay? So from there, we're going to break it down a lot further. We're going to make it a little easier to understand. There's certain things about electrical circuits, especially electrical circuits, that you need to understand when it comes to watts and how to calculate watts and how to calculate voltage and amperage if you have a known amount of wattage. So we're going to get into that a little deeper and make that hopefully a little clearer. And then hopefully wrap this thing up before too awful long, because these videos have been running kind of long. But I'm going to try to keep it under an hour if I can. We'll see how it works out. Okay, so here we are again at the whiteboard. All right, first thing I want to touch on, International System of Units, or units of measure. What does it mean? Where does that come from? Here's what I want you to know. As an example, okay, here's some International System of Units. As what I'm getting at here is the example is this. So the physical quantity is frequency. All right, that's been agreed upon internationally, right, as hertz or capital H with a small z. All right, for example, let's break it down, or the watt, what we're talking about today. The definition for power is the watt, capital W, right, or the volt, electric potential difference, or electromotive force, or voltage. The unit is volt, capital V. And the ohm, right, electrical resistance or reactance, the term or the unit is ohm, uses the Greek letter omega. Okay? And it goes on and on and on. There are many more for all different things. For example, for capacities, right? For what they call base units, meter, a second, a kilogram, ampere, which is the capital letter A for electric current. And like I said, there are several of them. Volume, right? Mass and weight. Anyways, they're just units of measure that have been agreed upon internationally, so that everybody recognizes the same symbols, the same terminology. If not, imagine if every country, for example, had their own terminology for a volt, or their own terminology and symbol for an amp or an ampere. You know, so in this case, if you're from England, Australia, United States, Canada, wherever you're from, same symbols, same units of measure. Makes things easier for all of us to understand. So that's what it means. That's what that's all about. You'll see when you see SI, that means that the watt is an international system of units or a unit of measure for power. SI is watt for power. That's all that really means. I just wanted to lay it out there so you understand. And like I said, if you want to look into that a little deeper, international system of units, you can look it up and find out when it was created and why they created it and what the organization was all about. It's kind of interesting, I guess, but at least it gives you an idea of where it comes from. When I say like capital E or capital V or capital A, it's not something I made up, right? Okay, so anyway, so let's move on a little bit. So the watt, there are two types of power, okay? Electrical power or mechanical power, right? Either way, both of which can be calculated into a watt. I gave you the concrete carry analogy, and that was mechanical power. But electrical power is a little bit harder to understand, but it's what we're talking about here today. Because we want to talk about, electric motors. If an electric motor is 1200 watts, what does that mean? If a light bulb is 80 watts, what does that mean? And we're going to talk a lot about power conversion and power consumption. All right. For example, we're going to convert electrical power. We're going to do a power conversion and make it mechanical power. I'll give you an example of that. You have a starter motor in your car that cranks your engine over, makes your engine rotate. All right. Well, it uses electrical power, current, amperage, voltage, and converts that into mechanical rotation to rotate the engine. So we've actually converted electrical power to mechanical power through the starter motor itself. Okay, so we've converted it. So now it becomes a little bit easier to understand how electrical power and mechanical power are related. And that is a power conversion. And then there is power consumption, meaning, as we had talked about with Kirchhoff's circuit laws, right? If a circuit is determined to be a 1200 watt circuit, right? 1200 watts going to a starter motor. right? We're going to calculate that into voltage and amperage, and then we'll talk about actual power consumption. All right, so when you see a wattage rating, right? Like for example, if something's rated at 80 watts or it's rated at 1200 watts, right? What you're basically seeing is a power consumption specification. How much power that circuit is going to utilize when it's functioning, okay? When you make a power consumption calculation, you are calculating for a wattage value. For example, if we take voltage and amperage and multiply them together to come up with watts, right? Because watts equals volts times amps, right? We're taking electrical pressure multiplied by the current flowing through the circuit, and we're gonna calculate that as a wattage value. So power consumption calculation, voltage pressure, and amperage flow or current flow or volume of flow is going to equal a wattage value. Okay, and a wattage rating is a power consumption specification. So if you know the wattage, you can then say if we have 12 volts, we know what the amperage must be because we can calculate it. Okay, so wattage rating, power consumption specification, power consumption calculation will equal a wattage value. So we can come up with a wattage value, or we can take the wattage rating and determine the power consumption specifications of voltage and amperage. All right, so electrical power, the rate at which electrical energy is transferred or consumed, right? So for example, if it was 80 watts or 240 watts, we would know that 240 watts consumes 3 times the electrical energy is going to be transferred or consumed. Mechanical power, the rate at which work is performed. We did the concrete carry analogy and actually showed you the rate at which the work was performed, how one person did it 4 times faster than another or twice as fast as another, and of course the rate was different between them, and obviously the mechanical power differences could then be or was demonstrated in that analogy. All right, so let's move on just a little bit further and let's talk about the joule. All right, now here's what this means. For example, let's say you have an 80 watt circuit, right? It's 80 watts. Or a 250 watt circuit. Let's say that this 250 watt circuit, let's say that is every light in your vehicle. You turn on the lights and you put it on high beams. And the total wattage of all the bulbs in the entire vehicle, right, comes out to 250 watts. Let's say you left that on for 2 seconds, right? That would then be 500 joules or 500 watt seconds. All right, so let's just break that down a little bit further. So what is a joule? A joule is 1 watt per second, or a watt second, right? So whether I said joule or I said watt seconds, I would be saying the same thing to you. They're interchangeable, right? This is not accepted. Like I wouldn't say that has 250 watt seconds. You'd be like, oh, you mean joules, if you knew what I was talking about, right? But it is the same thing. So for example, if I had 250 watts for 2 seconds, that'd be 500 watt seconds or 500 joules. If I had 250 watts for 4 seconds, that'd be 1,000 watt seconds or 1,000 joules. Basically what that means is, like I said, let's go back to the lights. If I turn your headlights on all the headlights, high beams, low beams, everything's turned on, off, right? But if I turn them on and leave them on for 30 seconds, obviously I've consumed a lot more energy in 30 seconds than I did in that 1 or 2 seconds when I turned them on briefly, right? So we want to calculate for that. So we know the wattage, but now we need to know the amount of time. So by knowing the wattage and by knowing the time, we can come up with a unit of measure known as the joule, or the watt seconds, watts per second, or how many watts per seconds, right? So if you have 250 in 4 seconds or 250 in 8 seconds, right? 8 seconds twice as much as 4, twice as much watts seconds, or twice as many joules, which is total electrical energy consumed. Okay, so your joule is your total energy, electrical energy consumed, in total, right? A watt is a rating of basically current flow per second. 1 watt is 1 watt per second is 1 watt, or 1 joule, right? 1 watt second or 1 joule. 1 watt for 1 second. If this was 250 watts for 1 second, it'd be 250 joules. 80 watts for 1 second, 80 joules, or 80 watt seconds, okay? So just think of it as this. A joule is the total electrical energy consumed. And think about the headlight analogy, right? How long they leave them on compared to a brief amount of time or a long amount of time, right? One's obviously going to be greater than the other, right? Okay, so basically, like I said, so what we're going to do from here is we're going to do the power conversion. We're going to do the power consumption. So think about this when I say power conversion. Think about it another way. Let's say that you have a power window motor. So obviously it's a power window motor, so it's got an electric motor. We're going to use voltage and amperage to power the motor. We're going to take that motor, turn it into rotational force, and drive a cable or a gear-to-gear mechanism, regulator, something to make that window go up and down. But think about, let's say that I had a rope. There was no electrical motor whatsoever, and I physically had a rope down inside the door holding onto the glass, and I pulled the rope up, and I held it up, and then we taped it there so the window couldn't go down. Well, I performed the work, the mechanical work that electrical power is going to be converted into, right? So the work I performed is the work that gets performed, but we do it through an electric motor, and we convert electrical power to mechanical power and drive that window up, right? So that's how it's converted from one to the other, if you think about it. But let's look at it one other way. What's another form of power conversion, right? You can take power and convert it into heat and light. As an example, if we turn a light bulb on, right, it produces light, right? Well, we use electrical energy to turn, we convert electrical power into light and heat. And there's heat. If you grab the bulb, you'll know, depending on the bulb, it's going to get extremely hot, right? Some get a little bit hot, some get extremely hot, depending on the watt rating of the bulb, right? So we've converted electrical power into light and heat. So it's still converted. It didn't remain electricity. It actually got converted into something useful, right? In that situation, it was light and heat is what it was converted into. The heat's a byproduct, but it is what it is. When the filament inside the bulb starts to glow, it puts off a certain amount of heat. The bulb itself physically gets hotter. So not only have we produced light, we've also produced heat. So light and heat is the conversion. So we made a power conversion, but not into mechanical power, but instead into light and heat, right? So I think that's really what I need you to understand here. From here, what I'm going to do is I'm going to break it down further. And if there's something else I need to mention as I do this, I'll bring it up. But I'm now going to basically get rid of all this, and I'm going to make some calculations. And we're going to talk about how when you calculate amperage and voltage from wattage, that the answer that you come up with, although accurate, might get you in trouble, okay? Because there are a few things you got to know about inrush current, and also known as surge current, that we're going to have to discuss, okay? And like I said earlier, I'm going to give you another breakdown. In fact, I'll do that first, of the horsepower calculation, and how the horsepower, when we say watts equals force times velocity, how that relates to horsepower. Okay, so that's what I'm going to do, but I'm going to clear this off to do that. So be back with you in 1 second. Okay, so here we are with our horsepower analogy. Earlier we had stated, in order to make this a little more clear, the equation power, or watts, equals force times velocity. We're going to use the calculation of the equation for horsepower. And I'm going to replace a few of these things. I'm going to swap out force for torque and whatnot, and you'll see what I'm going to do here. And hopefully this will make a little bit more sense to you. But let's say that we have an internal combustion engine, and we're going to take it down to the engine dynamometer, and we're going to have it tested. We want to find out how much torque and horsepower it's producing. Okay, well, first thing we have to know is that a dynamometer is a torque measurement device. It does not actually measure horsepower. It calculates horsepower from torque. The horsepower is calculated through its internal software, through the computer system, the control unit that's with it, whatever it might be. It's not measured directly. Torque is all that it measures, okay? That's what you gotta know about a dynamometer. So, let's look at our equation. Watts, or power, is equal to force times velocity, all right? So in this situation, we're gonna replace force with torque. And the reason we can do that is because the definition for torque is a twisting force. And in this situation, the twisting force is the rotational force acting upon the crankshaft. The actual twisting force acting on the crankshaft, right? The velocity is, as we had stated earlier, was displacement over time, is the definition for velocity. So the velocity here is revolutions of the crankshaft. Think about a revolution as a distance that it traveled. So the revolutions of that crankshaft over time, or per minute. So our velocity is revolutions per minute, which is crankshaft speed. All right, so now we basically have replaced velocity with crankshaft speed and force with rotational force acting upon the crankshaft, or torque. So now we can go to our horsepower equation. Horsepower is equal to torque times revolutions per minute divided by the constant 5252. So let's do a real quick calculation, let's say we were at the engine dyno, and a dynamometer itself measured torque at 400 foot-pounds of torque, and it occurred at 2,626 revolutions per minute. It would then calculate the horsepower at 200 horsepower. Same scenario, different engine, let's say. The dynamometer measured 400 foot-pounds of torque, but that occurred at 5,252 RPMs. That would then equate to 400 horsepower. And if yet a different engine measured 400 foot-pounds of torque at 7,878 RPMs, the calculation would then be 600 horsepower. So basically, this is my horsepower analogy for the equation power, or watts, is equal to force times velocity. One thing I want to leave you with on this is that watts equals horsepower, right? Plain and simple. They are interchangeable. They can be converted one to the other. Watts to horsepower or horsepower to watts. There is a conversion that you can do for that. In a later video, when we get to talking about a lot of the different calculations, conversions between, let's say, English and metric, or imperial standards and metric standards, like we talked about earlier, we talked about kilopascals and hectopascals and PSI and bar and atmosphere, and we're going to be converting a lot of these things back and forth in a video that's going to be based on just that. And when we do that, we will bring up watts and horsepower again, and how they convert, and what one and how it was how that conversion came about. How was that created, and that'll help make more sense as to how something that is, when we speak of watts in electricity, we're talking about voltage, which is electrical pressure, electromotive force, and amperage. How does that equate in the equation to horsepower? And it has to do with, as we had talked about earlier, power conversion from one to another, from, let's say, electrical power to mechanical power. But anyways, I'm kind of getting off the subject a little bit there. But that is my analogy or explanation for watts or power is equal to force times velocity, and how this fits the bill to help understand that a little bit better. All right, so from there we'll move on. Okay, so on to the wattage calculations. Since we have gone over Watt's law and the equations for Watt's law, and we've gone over Ohm's law and the equations for Ohm's law, should be pretty straightforward, right? So let's just see if that's the case. I'll give you two examples here. One's a 60-watt bulb. A 60-watt bulb in a 12-volt system, knowing Watt's law, right? 60 watts divided by 12 volts means that that system must be utilizing 5 amperes or amps of current flow. Okay, simple enough, right? 60-watt bulb, it's rated, says it right on the bulb. We know it's a 12-volt system, must be 5 amps. Plain and simple. So from there, we're using Ohm's law. We'll calculate the resistance in the circuit. So the Ohm's value will be 12 volts divided by 5 amps. Must mean that the resistance of that bulb must be 2.4 ohms. Okay, all right, simple enough, right? Okay, let's move on to the starter motor. Got a 1500 watt starter motor. It's rated at 1500 watts. It's in a 12 volt system. Do the calculation. 1500 watts divided by 12 volts. We have 125 amps. Also, simple enough, right? We're done. That's all we need to know. Well, unfortunately, it's just not quite that easy. So let's go over these 4 terms, the electrical system terms, right, or electrical engineering terms, and we're going to see how they work together. Just like a hand, they go together like a hand and glove, right? So the first one is inrush current. That's also known as surge current. Okay. Second one is locked rotor current. And the third one is back electromotive force or back voltage, because we had said before when we were discussing Ohm's law, the electromotive force is known as voltage, right? So back voltage would be accurate, right? And then a PTC or PTC resistor. PTC means positive temperature coefficient. So what does that mean? Basically, if we had a resistor or a resistance of any type, as the temperature of that resistor goes up, so does the resistance. For example, let's say we calculate the resistance at 1 ohm. We raise the temperature 50 degrees Celsius, right? Instead of it being 1 ohm, it might be 10 ohms. Right, so there's a drastic difference in resistance as the temperature goes up. All right, so we need to know this. PTC resistor, positive temperature coefficient. We need to know about back electromotive force or back voltage, locked rotor current. Now, locked rotor current and back electromotive force or back voltage are related to electric motors, right? In this particular situation, the PTC resistor is going to be related to our bulb, and inrush current is actually a heading for locked rotor current and PTC resistor. Inrush current is going to be related in this example. Inrush current is the same thing as saying locked rotor current and electric motor, or in the case of the bulb, is the same thing as current flowing through a PTC resistor. All right. So inrush current, what does that mean? What that basically means is that, let's say I have a circuit and it's calculated at, pick a value, I don't know, 1200 watts. So we're going to do the calculation. 1200 watts divided by 12 volts is 100 amps. Okay, well, that is when the circuit is operating. It's not initiating, it's operating. Now, when a circuit first initiates, whether it be an electric motor or a bulb or what have you, that current value can be much greater. As that circuit initiates, you may find out, due to the fact that it's a PTC resistor, or maybe the effect of what they call locked rotor current, that the inrush current is much greater. So if you were to monitor the inrush current, it would look like this, and then it would taper off, and then it would just normalize, and that would be your current or your rated value. Let's say 1200 watts, that would be your rated value. But your inrush current can be much greater than that, much greater. So let's break this down as far as the bulb and the starter motor that we have here. So in a bulb, as an example, we had said that since we know it's a 60 watt bulb, we know it's a 12 volt system, we determine it must be 5 amps of current flow through that bulb. Okay, all right, at 12 volts. So we went ahead and calculated the ohms or the resistance. We said 12 volts divided by 5 amps is going to be a 2.4 ohm resistance. Now, if I were to take a 60 watt bulb and check it with an ohm meter, right, what I'm actually going to get is not 2.4 ohms. I'm going to get about 0.24 ohms, or about 10 times less resistance. Now, as we discussed previously, we were talking about Ohm's law, is that if we have 10 times less resistance, then instead of having 5 amps flowing through that circuit, we're going to have 50 amps. All right, so wow, 50 amps at 12 volts, that would be not 60 watts, that would be 600 watts. All right, so that is accurate. And here's why I bring this up. If you were designing the circuit, and instead of actually measuring the wattage or the amperage, not measuring the wattage, measuring the amperage and calculating the wattage, right? Instead of it doing it that way, you just said, well, I'm going to go ahead and just check the resistance of that bulb, and I'm going to calculate the amperage, and then figure what my wattage would be. You're going to be very inaccurate, because you're going to check it with an ohm meter. The bulb is going to be cold. The filament, the tungsten filament inside the bulb, in most cases tungsten filament inside the bulb, is going to measure a very, very low resistance, which is going to give you a very, very high amp rating through that circuit. Well, okay, so here's the, and you need to know that if you're trying to calculate it. But here's the saving grace. Although that is accurate, and that does occur, that inrush current only happens for a brief millisecond. Without actually measuring it, the amount of time is extremely small. It is in milliseconds. It's so quick. That filament inside the bulb heats up so fast, and the resistance goes up so fast, that inrush current happens for such a brief period of time that you don't really have to design anything to be able, you don't have to design the circuit or the circuit protection, the fuse or the circuit breaker to handle a 50 amp current load. Because it happens for such a brief amount of time that it's not going to create a problem, right? Now, and that's the beauty of that. Now, to say that you're going to design the circuit to only carry 5 amps, well, you wouldn't want to do that. You need to design it and have a buffer. Have an air of protection, built into the circuit to where it's more than capable of carrying the load. It sure doesn't need to carry 50 amps, but it's got to be able to carry more than 5 amps, okay? So what I'm saying to you is this. If you calculated, if you just took a 60 watt bulb, you had it in your hand, you saw that it said 60 watts, and you calculated everything out, right? And then from there you said, well, let me go ahead and actually check the bulb and see what the resistance is. You'd say, well, dang, that guy on YouTube, he's lost his mind. This ain't got 2.4 ohms resistance. It's got 0.24 ohms resistance. And that guy don't know what he's talking about. But like I said, this bulb is going to act like a PTC, positive temperature coefficient resistor. and the resistance goes up rapidly with a rise in temperature. And as you know, if you ever watched a halogen bulb or any type of bulb, as soon as you turn the power on, as soon as the current flows through that bulb, it becomes bright immediately. Well, that's how fast the resistance goes down. I mean, the resistance goes up and the amperage flow goes down. So the current flowing through that bulb, although the inrush current is very high, it's for such a small amount of time that has very little impact on the remainder of the circuit. But something you need to know about if you're actually checking bulbs and calculating resistances, or not resistance, but amp flow or wattage, you will find out that your initial calculation will not be correct. Right? That'll be your inrush calculation, but not your operating calculation. All right? So let's move on. And like I said, the filament itself inside the bulb is going to behave like a PTC resistor. That's exactly what it behaves like. All right, so we still have inrush current going on in electric motors. Same thing, like I said before, locked rotor current and BEMF, back electromotive force, back voltage, right, is going to affect the operation or your calculations for these electric motors, right? So that being said, here we have a 1500 watt starter motor, okay? We know, okay, we got a 1500 watt starter motor in a 12 volt system. Well, that means that the current flow through that starter motor is 125 amps. We're good to go. That's all we need to know. It's absolutely incorrect. So what you need to know about electric motors, a couple different things. One is there's a phenomenon, or I don't know if I'd call it a phenomenon, but definitely an electrical term of locked rotor current. All right, so the rotating portion of the electric motor is called a rotor. That's the rotating portion of it. And when it's still, it's sitting at rest, it's called locked rotor. It's not rotating yet. So in order to get that rotor from a state of rest, where there's no movement, up to speed, towards its normal operating speed, right? The amount of current, amperage flowing through the electrical circuit in the motor, the starter motor, is going to be much greater than what you have calculated. Okay? And that is going to be your inrush current. Now, I have heard it said, and I've read that it can be as high as 10 times. So, for example, if you calculate, right, by knowing the wattage and the system voltage, then that's going to be 125 amp current flow through that circuit. They're saying that could be as high as 1250 amps. Now, I'm not saying that's not possible, but I have monitored that and measured that over the years. Normally what I see is something between 2 and 5 times, and usually more like 2.5 or 3. But even at 2 times, our calculation was 125 amps, right? So 2 times that would be 250 amps of current flow. Well, let's say 3 times that would be 375 amps of current flow. Now, in order to properly design the electrical circuit that is going to this starter motor, we have to design it in such a way that it can carry that inrush current. Because unlike the bulb, which has inrush current for just a millisecond, a brief amount of time, extremely small amount of time, the starter motor, as a good example, is not like that. I mean, if you've ever been in a car and you went to start the car and it went, the starter motor is turning very slowly, right? So that locked rotor current, or almost locked rotor current, is going to be much greater than 125 amps. So let's say when it first starts to turn the engine over, it's at 3 times, 375 amps. Now it starts to turning it over, it still might be 300 or 275 or some value much greater than that. If, on the other hand, you went to crank the engine over and the engine cranked over, or spinning over fast, no, just spinning over just fast as it could be, then maybe you might be somewhere in 125 amps or 1500 watt range. Maybe that's possible. It's not impossible for sure. So your inrush current is going to be really great. To go from 125 to 375, you're going to have to design the circuit in such a way that it can handle that kind of amperage flow. Because like we said before, amperage is volume of current. Like we talked about the water flow from the water tower, the pipes get larger and larger, they flow more and more water, right? So in electrical circuits, the wire, the actual conductor, the wire itself, must physically get larger. So for example, if you said to yourself, well, 125 amps of current flow, I probably could get away with a 2-gauge wire. That should be more than sufficient. In reality, you may actually need a 1-gauge wire or even a 1-aught wire, which is even just gets larger and larger, depending on the distance of the wire, how long the wire is going to be, right? But you may find that designing that circuit for 125 amps is going to be drastically insufficient. You know, you're going to have to be considerably larger as far as wire gauge. The protection for that circuit, whether it be a fuse or a circuit breaker or whatever, is going to have to be a lot greater than 125 amps, right? So there's another phenomenon that occurs. For example, if you, and you may or may not have ever done this, but if you ever did a bench test on a starter motor, just as an example, and you hooked up positive to it, like right from a battery or a battery source or a power supply, you'll see that the starter motor engages and spins, but it only gets to a certain speed. It doesn't blow itself apart. It doesn't just continually go faster and faster and faster and faster until finally it just flies apart. It doesn't do that. It gets to a certain speed and it just kind of sits there. You know, have you ever thought about why that is? You know, why does it have that speed limiting capability? Why doesn't it just keep going faster and faster and faster? Okay, now there is a phenomenon that is known as back electromotive force. Okay, and what that means is that as that electric motor is turning, that starter motor or fan motor or whatever motor it is, as it's spinning, once it gets up and starts rotating, as it speeds up, it starts to generate its own voltage. It starts to act like a generator and actually produces its own current and voltage. So they call that back electromotive force. So if we have current flowing through the starter motor in order to get it to rotate, right, we have amperage and voltage flowing through it, you know, which is measured as watts, amperage and voltage, flowing through the motor, through the starter motor, rotating it, creating enough electrical energy and power to crank the engine over, but now it's spinning over it at a decent amount of speed, right? It's actually spinning quite fast. Now, the starter motor itself starts to produce its own voltage. So imagine if you had 12 volts coming in, and let's say you had, just as an example, 12 volts coming in, you had 2 volts coming out, right? And they're opposing each other, right? So now the current flow through the starter motor reduces, right? Because it's producing its own electrical voltage and amperage or current, right? Current flow, and they're opposing each other. So if you were to monitor this circuit, what you will see is that let's say we're using an inductive ammeter and we are monitoring the amperage flow to that starter motor, what you would see is you'll see an inrush current where there's a lot of amperage flowing into the starter motor, and then as it began to rotate, you would see it start to come down, and as it got up to speed, it would come down to a certain level and then level off. Okay, when it levels off, what you are seeing is the amount of current flowing into the starter motor, the amperage and voltage, and at the same time, the current that's opposing it or reducing it. So what you're seeing is the net effect, the total coming in, but the amount of back current or back voltage that it's meeting. So now you have a leveled off amount of current and voltage. Okay, so in I don't know about layman's terms, but in commonly referred to, I would say, as a speed limiter. It's the reason why when you do a bench test on a starter motor, it doesn't just go faster and faster and faster and faster and faster, because as it speeds up and it starts producing its own electrical voltage and current and amperage and current, overall current, it starts to oppose the incoming electrical voltage and amperage or current, and it regulates, it like self-regulates. Okay, and at that point it basically acts as a speed limiter. That's why it doesn't just keep going faster and faster and faster and faster and faster. So what I'm getting at is this: in an electrical motor situation, if all you did was take 1500 watts divided by 12 volts, you came out to 125 amps, you would be wildly inaccurate. Okay, you have to take into account locked rotor current, which is going to amount to your inrush current, right? And you have to take into account your back electromotive force, which reduces your current consumption. How do you do that? The best way to do it is to measure it. Okay, literally measure it. We had talked about in previous video, I believe it was video number 1, we had talked about inductive ammeters and inline ammeters. They literally measure the wattage. They measure the current flow through the circuit. That's your best way to know. But this is a really good, this 1500 watts is a really good starting point, right? 100%, it really is. So you could take what I'm telling you, for example, like if I was going to design a circuit and I was not able to measure the current flow in that circuit, right? I was not able to measure it. I would basically factor in, if this was a 125 amp circuit going to that starter motor, 1500 watt starter, 125 amps going to it, at least 125 amps. Okay, I'm probably going to factor in something in the order of about 2.5 times, maybe 3 times that much, so that my circuit can easily carry that kind of a load. Another thing to consider is that anytime you have an energy source like a battery and you are utilizing that energy source, this voltage, we had talked about voltage as voltage pressure, and a battery as an electrical energy storage device, right? As you utilize some of that energy, the pressure will drop some. So the voltage will drop. So a 1500 watt starter motor, if it were 12 volts while it was operating the starter, it would then be 125 amps, let's say. But let's say that the voltage drops down to 10, which, you don't want it to be that low, but let's say it were to drop to 10, just for discussion's sake. Now we got 150 watts, 1500 watts divided by 10 volts, now we got 150 amps, okay? So if that was the case, we had 150 amps, multiply that by 3, we got 450 amps of inrush current. So like I said, it's just something you have to take into consideration. Your best bet is you have to know going in roughly where you're going to be. If you're going to design an electrical circuit, you need to know roughly where these calculations are going to fall into. And I think that starter motors are the worst case scenario. And an example of that is this. If you have a engine cooling fan motor or a fuel pump, electric motor inside, an electric fuel pump, you can easily test those. You could bench test those before you ever install them on the car. But until the car is assembled, you got the engine in the car, starter motors attached to the engine, the actual engine that's going to be in the car, right? It's hard to test current flow through that starter motor because, as an example, if the engine itself is a big, large displacement, 500 cubic inches, 14 to 1, static compression, big race motor, it's going to create a lot more resistance to that starter motor rotating than it would if it was a 4-cylinder engine with low compression. So it's really hard to determine exactly what the locked rotor current is going to be until you have it installed on the vehicle. And like I said, starter motors is a worst case scenario because it is indicative or directly related to the engine that it's rotating. So it's a little bit tougher to design for that, something you have to take into consideration. But all other motors that come to mind anyway, like I said, like cooling fan motors, power window motors, power seat motors, electric fuel pump motors, electric water pump motors. You can bench test pretty much all of that and come up with a rating and use an inductive or an inline ammeter, and you'll know exactly what you're dealing with, and you can design a circuit around that, okay? So anyways, that's what I wanted to get to and how I wanted to discuss the importance of not only calculating converting watts into volts and amps, but also measuring it and why it's important to actually measure it whenever possible. And these are some of the things you have to take into consideration. All right? Okay, so let's finish it up here today with one last discussion about electrical energy, stored electrical energy, the rate at which we utilize or discharge our electrical energy, and for how long, the duration and time. I have 3 examples here behind me that I want to go over to kind of like wrap this up, give you something to think about, something you can wrap your mind around, something I like to say, right? And basically explain how 800 volts may be fatal to you, but maybe 50,000 volts won't be. I mean, how's that even possible? If 800 volts will kill you, then how come 50,000 volts won't? Which isn't to say that it won't, but in these examples you'll see why it's possible that they may not. Okay? So let's get to it real quick. First off, let's talk about static electricity. We've all been zapped by somebody, or we've zapped somebody, or we've discharged some electrical energy into anything, the table or some metal object or another person, and you felt that. It hurts a little bit, but it's not too bad. It sure ain't going to kill anybody, right? Or it hasn't that I'm aware of anyway. But so what's going on there? Well, what's happening is that your body, because of the interaction between your clothing and the carpet or the chair you were sitting in or whatever it might be, has created an electrical charge. Your body is acting as a capacitor. We'll just think of it as a battery that you can discharge extremely rapidly. You can charge it extremely rapidly and discharge it extremely rapidly. So that's basically in effect what you are. You become a capacitor, just a big walking capacitor, and you are charged with voltage. Right? And when you touch another individual or touch a metal object, whatever it might be, you discharge that voltage. Right? You rapidly discharge it. But, so, how much voltage is that? Well, In reality, it can be greater than 30,000 volts. Well, how come 30,000 volts? You think if you walked up to somebody and hit them with 30,000 volts, you'd kill them for sure, you know. Well, so why doesn't that kill somebody? Well, it has to do with the amount of energy that you have stored. You know, even though you are 30,000 volts, you haven't really stored that much overall energy. For example, if static electricity, when it discharges, it basically has a rating somewhere in the order of, and I did some research on this, 500 millijoules. And we had said before that a millijoule, or a joule, I'm sorry, is a watt second. 1 watt for 1 second. We're talking about 1/2 of 1 watt for 1 second, or 1 watt for a half a second, right? But a rating of only 500 millijoules. A very, very, very low energy rating. And on top of that, the duration of time that you just discharged that electrical charge that you're carrying around is in the order of 1/10 of a millisecond, 1/10 of 1/1000th of a second, or 100 microseconds. So yes, you are carrying around a lot of voltage, but you have very little energy, very little stored energy. So that the voltage, like I said before, think about an electrical battery, right, as a stored energy source, and voltage as pressure. And it's just dying to get out of there. It's just dying. You have a lot of force. It's just ready to go. It's ready to get to a path of least resistance, whatever that might be. Another person, it wants to discharge. It wants to move on, if you will, right? Electron flow, it wants to move on. So basically, you discharge into another individual and you zap them, and they're not very appreciative, but you did it, you know. But it was 30,000 volts, but it had very little electrical energy, and for a very, very short duration. So in that situation, that 30,000 volts didn't harm them at all, right? But let's say, for example, that you were charged with 100 times more energy. So instead of zapping them with basically, you know, 1/10 of a millisecond, let's say that you have 100 times more than that. Now you're zapping them for 10 milliseconds. Well, that's going to get, you know, that can become very, very dangerous. At some point, as that escalates, the joule rating will go up, the duration will go up, and it's going to become very, very, very dangerous. But in this situation, even though you are walking around at 30,000 volts, it's not actually all that dangerous. It's not going to kill anybody, right? All right, so let's move on. Let's go to an MSD system, a multiple spark discharge. This is a brand for anybody who doesn't know, MSD. 7AL-3 ignition control unit. It is what's called a CDI ignition system, capacitive discharge ignition. That's the type of ignition system that it is. It basically just means it has capacitors that are charged, internally charged, and then that energy is released. And so this is off of their website, right? And they show that the spark output from the ignition coil, which is controlled by the ignition control unit, is going to have a total of 50,000 volts, 160 millijoules, once again, 0.160 watt seconds or joules, for a duration of as long as 20 degrees of duration. So if you calculate that out, right, let's say the engine is running at 3,000 RPMs, 20 degrees of duration is only 1.11 milliseconds of actual spark output, right? The amperage is going to come out somewhere around 2.88 milliamps, very, very low, and the calculated wattage is going to be approximately 144 watts. So even though it is 50,000 volts, the total electrical energy is very, very low. The duration is in milliseconds, right? And the amperage, as I had stated, since the voltage is very, very high and the overall joule capacity is low, then you know the amperage must be very low, 2.88 milliamps. All right, so basically anybody who's ever been shocked by this, been, you know, accidentally shocked by this, it does hurt. It does hurt. And because of the amperage, because of the actual overall current flow, you're actually able to pull away from it. Now, since this engine is running at 3,000 RPMs, what I have calculated here, that's for one spark event. One spark event. But, as we know, the engine is running at 3,000 RPMs. It has multiple, one spark event after another, after another, after another, after another, right? 8-cylinder engine, 3,000 RPMs. You got thousands of sparks. So this is not going to happen just once. So this is not going to, like it does here, when you static electricity discharge. Once you've discharged, as you know, you walk up and touch somebody again, nothing. You've discharged. Well, this has a capacitors internal that are charged and discharged over and over and over and over again. So this repeats. So this can be very dangerous. If, for example, the car was running at 3,000 RPMs and you were working on it for whatever reason, and you fell on to the ignition coil or one of the wires, and it was zapping you nonstop, right? It could kill you. It could. But I've not heard of anybody being killed by it. I'm not saying it can't. If it did it repeatedly and you were in such a physical condition where you're greatly affected by even low current shocks or electrocution, it could kill you. Absolutely. But I've been hit by it, and a lot of people I know have been hit by it in other types of ignition systems too, and you are able to pull away from it, and it does hurt. It really does hurt. Anybody who's ever been hit by it, they know it hurts. Okay? So let's move on. Let's talk about another scenario, totally different. Here we have a 2025 Audi RS e-tron GT. Okay? And I worked on Audis for years. It's one of the reasons I bring this up. But this is their latest specifications. They show that it's an all-electric vehicle. It's their hot rod. It's the fastest thing that they make, as far as I know, at this point. They show their battery architecture to be 800 volts direct current DC. They show the usable capacity as 97,000 watt hours. Okay, so that basically means that it has the capacity of 97,000 watts for an hour, or 1 watt for 97,000 hours. And that sounds like I'm exaggerating, I know, but that's the reality of it. That's how large and how capable and how much energy is stored in that battery, right? Okay, so let's break that down to joules. Here we're talking about 0.5 joules, a half of 1 joule. Here we're talking about 0.16 joules, right? Just over a tenth of a joule, right? We're talking millijoules, just tiny, tiny amounts of stored electrical energy. This battery pack in this car, being it's 800 volts, has 97,000 watt hours, there's 3,600 seconds in an hour. So you take 3,600 seconds times 97,000, you come out with a total of 349,200,000 joules. So 349.2 megajoules, not millijoules, not a tenth of a joule, 349.2 million joules. Tremendous electrical energy, tremendous stored electrical energy. Not only that, the rate of discharge in this battery pack is tremendous. Okay, it can deliver tremendous amount of voltage and amperage, therefore wattage, in order to power the vehicle. You know, that's the reason they are so powerful and they are so fast, is because that battery can discharge that energy very rapidly at great volume. Okay, so let's take a look at something real quick here. Let's do a real quick calculation. The human body, the skin of the human body is not very conductive, has a lot of resistance. I checked mine the other day. I licked my fingers and I stuck my ohm meter between both probes between my fingers. I had about 55,000 ohms. That's a lot of resistance. That's through my skin from one path, whatever path it took to get from here to back to here. Right, it was calculated at 55,000 ohms. That's a lot of resistance, and that helps in situations like this to protect you from real quick zaps like that. It helps to protect you. But in this case, we have 800 volts of voltage pressure, and internally, once we get past the skin, our internal resistance is somewhere around 300 ohms. And 800 volts, it's in very short order, will penetrate the skin. And basically then you're left with your internal resistance, which is 300 ohms. And this is just a rough calculation. I didn't look this up anywhere. It's just something I just, took a pen and pencil, or a pen and paper and just kind of, figured it out right quick. But if it's 800 volts, we have 300 ohms of resistance. That means that we're going to pass 2.667 amps. I rounded it off. 2.667 amps. That means that 800 volts at 2.667 amps of current flow through our body is going to come out to 2,133.6 watts of current flow through our body. So 800 volts at 2.667 volts is going to be flowing through you. Now, this has tremendous capacity, right? A lot of stored energy. So let's break it down. If we're going to pass 2,133.6 watts through us, how long can it electrocute us? I mean, is it going to electrocute us for a second? 1/10 of a millisecond? Right? Is it going to electrocute us for 1.11 milliseconds? No. So basically you have 349.2 million watt seconds. 349.2 million watt seconds. That's going to electrocute us with 2133.6 watts. So if you do the math, take 349,200,000 divided by 2133.6, we'll find out how many seconds we have that it's going to electrocute us for. And you break that down into hours, that battery pack can electrocute us with 2133.6 watts for 45 hours, 28 minutes, and 33 seconds. By that time, there's nothing left of you. You know what I mean? Basically, after probably a few minutes, there ain't much left of you, let alone 45 hours. So, the amount of stored electrical energy in this battery, the amount of discharge, the rate at which it can discharge, the rate at which it can flow electrical current, right? You were only asking it to flow 2.66 amps. It can do that and never even blink. I mean, that's nothing. And it can do it for over 45 hours before it ever dies. So in this situation, it's not just the voltage, right? It's the amperage. It's the duration, right? Eventually, I mean, in a very, very short order, it'll kill you. Very, very short order. These have tremendous potential. They have 50,000 volts or 50,000 volts of pressure, right? But it's like, bang, and that's all I got. That's it. That's all I got. Like, oh, that hurt. You know, like, okay. As opposed to like being, hit repeatedly for 45 hours, right? Same thing up here. Whack! Oh, that hurt. I got 30,000 volts of pressure, and that's all I got though. That's all I got. And you were able to tolerate that because it only lasted for microseconds or milliseconds, so you can tolerate it. And the overall energy, the total volume, even for that split second, was very low, so you were able to tolerate it. In this situation, obviously, we're passing 2133.6 watts through us, 2.667 amps at 800 volts for 45 hours, right? There's no way of surviving this, no way whatsoever. But I just want to explain basically how 30,000 volts didn't kill you. And also it's interesting to know that static electricity, that you generated when you were a kid and you walked around zapping everybody, might have been as high as 30,000 or even more volts than that. That's kind of interesting to know. It's also interesting to know that your electrical system, your secondary ignition system, on your performance car, your hot rod, your race car, whatever, even though it's shown as 50,000 volts, the total energy there is actually kind of low. It has a lot of voltage pressure, not a whole lot of volume, not a whole lot of real, true stored energy. But since this recharges over and over and over, although a battery, this is just stored, just sitting there. Nothing's recharging it. This is recharging the entire time the car is running, or the engine's running. This continuously recharges. Non-stop, recharges, discharges. So this never really stops. So once it starts zapping you, it's going to continue to do it. And it can become very, very dangerous very, very quickly. But usually, like I said, you can pull away from it and you'll survive it. But this can kill you. If you fell on it and it kept zapping you, it potentially could kill you. There's no doubt. This I don't think has ever killed anybody. This can definitely start a fire, though. If you got a gas can, you have a bunch of fuel vapors. You can smell a lot of fuel in the air. And you just came in from outside, and it's wintertime, and you pull your sweater off, and sparks are flying everywhere. Have you ever done that in the dark? You pull your sweater off, and sparks are flying everywhere, and you happen to be hovering over top of a gas can, it might blow up. I mean, just keep that in mind, right? But you won't electrocute anybody with it. So that's basically what I've got for you for today. I think that kind of wraps up my last thought that I had. I'd like to take 1 minute here and just a second, actually, and just wrap this video up with one final thought. And that is, throughout our day-to-day lives, let's all try to remember to be thankful, to stay humble, and to be kind. Thanks for watching, and I'll see you on the next one.